Ideas for solving Rubik's Cube and related puzzles are discussed in this lecture. The cube has 6 faces of different colors. In this display, 3 sides are viewed directly and 3 sides are viewed as reflections. There are 9 squares on each face. The center squares remain fixed when faces are turned. Each corner square is part of a corner cube that has 3 faces. Each face of the cube also has 4 edge squares. Each edge square is part of an edge cube that has 2 faces. Fortran computer codes that allow the user to solve the cube and related puzzles by turning one face at a time may be downloaded at this website. This is the display for the Professor Cube. This is the display for the Nested Cube. This is the display for the Megaminx. This is the display for the Gigaminx. After turning the faces in a random order, the cube becomes scrambled as shown here. The cube is solved by returning the corner cubes and edge cubes to their proper positions and also making sure they are properly oriented. It's easy to use a freestyle approach to get some of the cubes into their proper positions and orientations, but it's very challenging to completely solve the cube with the freestyle approach. Once you get some of the cubes in place, it's difficult to get the remaining cubes in place without messing up what has already been done. In order to finish solving the cube, it helps to have moves that only affect a small number of cubes while leaving the others fixed. One way to find useful moves is to use basic concepts in group theory. We will discuss these ideas at an elementary level that doesn't require one to be a mathematician. Each configuration of the cube corresponds to a move, which is a permutation of the positions and orientations of the corner and edge cubes. The moves U and V consist of series of twists of the faces. The product U times V is defined to be the move that corresponds to applying U and then applying V. 2 moves commute if they correspond to the same configuration no matter which order they're applied. The inverse of a move corresponds to making the same series of twists but in opposite order and in opposite directions. The product of a move and its inverse is the identity move, in which every component of the puzzle remains in the same position. Here we are running the code for solving Rubik's Cube. The Fortran code is run in this window, and here is the display. Let's enter a 1 to rotate the left face, and then a 3 to rotate the top face. Refreshing the postscript, this is the result of these 2 moves. Now let's reset the cube and apply those moves in the opposite order. So first we'll enter a 3 and then a 1. And note that this is a different configuration of the cube. So these 2 moves do not commute. In order to illustrate an example of an inverse, let us first scramble the cube by entering a random series of turns. The negative numbers correspond to turns in the clockwise direction. The inverse consists of the same series of moves, but in the opposite direction and the opposite order. Applying the inverse has caused all of the corners and edges to return to their correct positions and orientations. It is convenient to use the cycle notation for permutations of the components of a puzzle. In this example, the permutation U is a 4 cycle in which A goes to B, B goes to C, C goes to D, and D goes to A to complete the cycle. In this notation, each entry in the parentheses goes to the entry that follows, and the last entry goes to the first entry. When U is applied again, there is a 2 cycle involving A and C, and a 2 cycle involving B and D. If a move consists of cycles of various lengths, raising it to a power might produce a move with a simple cycle structure. In this example, U consists of the product of a 3 cycle and a 2 cycle. If U is squared, the 2 cycle goes away and all that's left is a 3 cycle. If U is cubed, the 3 cycle goes away and all that's left is a 2 cycle. We enter 2 ones to rotate the left face by 180 degrees. And then we enter 2 threes to rotate the top face by 180 degrees. There are 2 cycles involving this pair of edges and this pair of edges. There are 3 cycles involving corners and edges along this row, and this row. One of the advantages of this code is that you can cut and paste moves and reproduce them. So now we have squared this move, and this is what we get. Note that the 2 cycles of edges go away. Now let's apply the move again. So now it's been cubed, and this is what we get. This simple move only involves a 2 cycle of these 2 edges and these 2 edges. Conjugation is a powerful approach for solving puzzles. A conjugate of U has the same cycle structure as U. When the conjugating move is applied, different components are moved into the positions that are affected by U. When U is applied, there is a permutation of these components according to the cycles of U. When the inverse of the conjugating move is applied, these components are returned to the original set of positions, but they are permuted among those positions according to the cycles of U. Let us illustrate some conjugates of this move. First, let's reset the cube. Let's consider a conjugating move that moves this edge to this position without disturbing this edge, or this edge. First, we rotate the back face. Then we rotate the right face 180 degrees. Then we invert the rotation of the back face. the edge that was here has now been moved to this position, and none of these three edges have been disturbed. We may now cut and paste the move This move has now swapped these edges and these edges. We now invert the conjugating move. This conjugation causes these two edges to be swapped and these two edges to be swapped. Note that the structure is the same as the original move. Now let's reset the cube and consider a different conjugation in which this edge moves to the same position but in a different orientation. We first rotate the top face, then the right face, and then we invert the rotation of the top face. We have moved the edge from this position to this position, but in a different orientation from the previous case. Once again, we cut and paste U. Now we have swapped these edges and these edges. Finally, we invert the conjugating move. This move swaps these two edges and it swaps these two edges while at the same time changing their orientations. Another approach for finding useful moves is based on the concept of a commutator of two moves. If U and V commute, the product of cycles in the commutator cancel out completely. The commutator may have a simple structure if there is partial canceling. Let's consider the commutator of turns of the left and top faces. The product of these moves has an effect on 13 cubes. Now we're entering the other factors in the commutator. The commutator has an effect on only 7 cubes. There are a 2 cycle of these corner cubes, a 2 cycle of these corner cubes, a 3 cycle of these edges, and orientation is also affected. Let's ignore the effect on the edges and look for a useful move for the corners. A yellow square went from here to here. An orange square went from here to here. The other orange square went from here to here. A green square went from here to here. A blue square went from here to here. The other blue square went from here to complete a 6 cycle. There is a similar 6 cycle involving the faces of these corner cubes. If the move is squared, we obtain 3 cycles that correspond to rotations of 4 corner cubes. Let us cut and paste to square the move. These 2 corners have been rotated counterclockwise. These 2 corners have been rotated clockwise. Multiple applications of this move and its conjugates are sufficient to get all of the corner cubes oriented properly. Corner cubes A and C may be swapped with a series of counterclockwise turns of the left, top, front, right, and back faces. This move and its conjugates may be used to get all of the corner cubes into the correct positions. Rubik's Cube may then be solved by using the moves for rotating the corners and moving the edges that we have already discussed. This is the configuration after applying the move. Corners A and C have been swapped. Another approach for generating useful moves is to apply a conjugating move that affects only one item in a face, rotate that face, invert the conjugating move, and then invert the rotation of the face. Let's use this approach to generate a 3 cycle of corners in the Megaminx. We want to replace this corner by rotating the green and red faces. So the corner has been moved out of the top face. A new corner has been moved into this position. And now a different corner is in the top face. If we were to invert the conjugating move at this point, this corner and the one that it replaced would be returned to their original positions. But we instead apply a turn of the top face, which moves another corner into that position. So now another corner from the top face has been moved into this position. Now we invert the conjugating move. Finally, we invert the rotation of the top face. We have a 3 cycle of corners. Let us apply a similar approach to rotate 2 corners. We want to move this corner down to the bottom of the driveway along this path. So now this corner is in this position. Now we want to back it out of the driveway by turning this face so that it will have a change in orientation. So now it has been backed out of the driveway. And now we want to move it back up into the top face. So now this corner, instead of being replaced, it has a different orientation. If we were to invert the conjugating move at this point, we would simply be returning this corner to its original orientation. But instead, we rotate the top face. Now we have moved a different corner into this position. And now when we invert the conjugating move, we rotate this corner in the opposite direction. And now finally, we also invert the rotation of the top face. This move causes two corners to be rotated. Now let us apply this approach to generate a 3-cycle of edges. We first turn the yellow and green faces so that the corners will not be disturbed. The corners have now been moved out of the way. Now we turn the orange face to move a different edge into this slot. Now we turn back the yellow and green faces to return the corners to their correct positions. This edge is the only item in the top face that has been affected. So we rotate the top face. Now we invert the conjugating move. And finally, we invert the rotation of the top face. And so we have a 3-cycle of edges. Let's apply this move again by cutting and pasting. And so we get a different 3-cycle. And if we apply it again, we have the identity. Now let us apply the approach to construct a move for flipping 2 edges. Once again, we begin by rotating the yellow and green faces to get the corners out of the way. And we rotate the orange face to bring the edge to this position. We now rotate the purple and red faces to pull into the driveway and back out and change the orientation. We rotate the orange face again to return the edge to the top face. Now we turn the yellow and green faces to move the other pieces back into place in the top face. This edge is the only item in the top face that has been affected. We rotate the top face, and now we're going to invert the conjugate, which will flip the orientation of this edge. Finally, we invert the rotation of the top face. And there we have a move that flips two edges. These four moves and their conjugates are sufficient to solve the Megaminx. The approach for generating useful moves for the Megaminx is also applicable to the Professor Cube. The approach is used here to derive a 3-cycle of inner edge squares. After applying the conjugating move, only one square has been modified in the top face in the image on the lower left. After turning the top face, inverting the conjugating move, and inverting the turn of the top face, we have the 3-cycle on the lower right. Note that the yellow square marked by an arrow is part of the 3-cycle. The approach is used here to derive a 3-cycle of inner corner squares. After applying the conjugating move, only one square has been modified in the top face in the image on the lower left. After turning the top face, inverting the conjugating move, and inverting the turn of the top face, we have the 3-cycle on the lower right. Note that the yellow square marked by an arrow is part of the 3-cycle. The approach is used here to derive a 3-cycle of outer edge cubes. After applying the conjugating move, only one square has been modified in the top face in the image on the lower left. After turning the top face, inverting the conjugating move, and inverting the turn of the top face, we have the 3-cycle on the lower right.